Thank you for joining today's talk. My name is Muyi Zhang, and as Bob introduced, I'm from Linköping University in Sweden, and I'm also very excited to be the first speaker with the topic of perovskite LED. So today, I'm going to share with you our recent work with the title of Towards a Sustainable Commercialization of Perovskite LEDs. So we will be talking about how to design these fancy materials, perovskites, out of the lab and into real life products from a sustainable perspective. Our focus will not only be on the technical progress on these devices, but also on the environmental and economic viability. So let's start. So we start from the utilization of light in human society. So we all know that humans have been using light for tens of thousands of years. Back in the prehistoric era, actually people use torches to light. Then during the medieval period, oil lamps become common. And later on, with the invention of electricity, we started using light bulbs. And today, we have light-emitting diodes, or LEDs. At the same time, the way we use light has become much more efficient. The luminance efficiency has improved from just 0.1 lumens per watt to over 300 lumens per watt. So we can clearly see this trend. The more advanced our use of light, the more advanced our society becomes. Now let's take a closer look at LEDs, which have become a central part of our modern lives. As we know, LEDs are devices that convert electricity into light. They are used in everything from general lighting and digital displays to optical communication. Compared to the traditional light sources, LEDs offer much higher efficiency. Meaning we get more light while consuming less energy. That's why they have become so important in the global push for energy-saving solutions. They also provide better color rendering, which is important for things like high-end displays, and they offer better flexibility. LED really changed our life, and the Japanese scientists were awarded the 2014 Nobel Prize in Physics because they invented the 3-5 semiconductor LED, which is a gallium nitride LED. Nowadays, we have used OLED, which is already common in TVs and smartphones. And in recent several years, we can even purchase the foldable smartphone from the shop. Like this video, I think is based on OLED screen. It's really fancy. The only problem is it's expensive, so I haven't bought it. And this is also the motivation why we want to develop perovskite LED, because we think perovskite LED could be cheaper. Now let's take a look at how LED actually work, what's happening inside. So here in the picture of a common LED product, which you can buy from a shop. If we cut it open, we can see the device structure inside. We have a simple device structure. It usually has a P-type semiconductor layer and N-type semiconductor layer. And in between, we have the emissive layer. That's where the lighting happens. When we apply current, electrons and holes are injected from both sides, and they're meeting in this layer. When they recombine, they release energy in the form of light. And we call this process as electron luminescence. And depending on the materials we use in this emissive layer, we get different types of LEDs. For example, if we use 3-5 semiconductors like gallium nitride, we get traditional 3-5 semiconductor LED. If we use organics, we get OLEDs. And if we use quantum dots, we get QD LED. And of course, if we use perovskite for the emissive layer, we get so-called PeLED. I understand that most of our audience today are solar cell background. So I make a table to show the comparison between LEDs and PVs. So basically, LED and PVs share a similar structure. They both have a p-n junction, but they work in opposite directions. LED turns electricity into light, and the solar cell do the opposite, light into electricity. And LED inject the holes and electrons, while PVs separate them. So they are like currents working on different shifts. Some important parameters for LEDs are external quantum efficiency, power conversion efficiency, brightness, T50 lifetime. And for PVs, they are PCE and T90 lifetime. And I would like to briefly introduce some key parameters that we usually use to evaluate LED performance. So this table might look a bit intense, but it's actually pretty straightforward to understand. So first, we have the external quantum efficiency, EQE. It tells us how many photons we can get from every electron we put in. And the real-world LED product never, although the real-world LED product never use EQE, but we scientists really love this parameter because it is able to reflect the physical design limit. And next is the luminance, measured in candlelight per square meter. So this is how bright the light appears to the human eye. And then we have radiance, which is more about the optical power density. This one is especially important for near-infrared LED, where human eyes cannot see. And now when we talk about how efficient our light is, we look at the lumen power efficiency, measured in lumens per watt. And this tells us how well we are converting electrical power into visible light. And then there's PCE, which is power conversion efficiency, the same term as PV. But and this term is more about total energy, how many watts of light we get per watt of electricity. And finally, there's a T50 lifetime, which simply means how long it takes before the brightness drops to half of its original brightness. So it's one of the key parameters. That's when people ask how long will your LED last, then T50 lifetime is your answer. I also include a small table to compare how EQE is defined in LEDs and PVs because they are quite different. So in PVs, EQE means electrons out per photon in, but in LED, it means photons out per electron in. The same term, but very different perspective. One more important thing is that the thickness of perovskite layer are very different in LED and PVs. Normally, it is hundreds of nanometers in PVs, but tens of nanometers in LEDs. And this could cause a large difference in materials impacts. And of course, when we talk about LED, we always clarify the color or the wavelength, because the different color, blue, green, red, white, or near-infrared, they play roles in different applications, and they demonstrate very different performance among different wavelengths. Now let's talk about perovskites, the material behind PLEDs, even though I know that most of you guys haven't been very familiar with these materials. So perovskite is a type of semiconductor with a structure of AbX3, as shown on the right. And what is special in that is by simply changing the elements A or B or X, we can tune their properties quite easily. So for LEDs, perovskites offer a lot of great advantages. Firstly, they have a tunable spectrum. We can get from blue to near-infrared light from the same material system just by changing some cathodes or the halide side. And second, they emit very narrow full width at half maximum, which means beta color purity. And third, the POQY can be really high. And as we discussed earlier, that directly help boost EQE. Also, they are solution processable, and which makes them cheaper and easier to manufacture compared to the traditional 3-5 semiconductor LEDs. And finally, they work well in both PI and IP structures. So altogether, these features make perovskites very promising for the next generation of LEDs. And this graph shows how far PLD have come in just on the 10 years. The axis is a year starting from 2014 when the first PLD was invented by contender and Richard Friend. At that time, the EQE was only around 3.4% for near-infrared and just 0.4% for green LED. So it was a pretty humble beginning, but things just changed very quickly. So if we follow the curves, so we can see how fast the field progressed. We have had three major development stages. The first focused on getting any emissions. The second was about boosting EQE. And the third, which we are in now, is about pushing both EQE and the lifetime upward. So this beautiful figure shows up to the year of 2022. Green had taken the lead, reaching over 25% EQE and even cracking the 10,000 hour mark for the lifetime. But blue is still the most challenging. Just like in OLED, they demonstrate a lower EQE and lifetime. But the progress is also clear. And we believe with more people working on it, maybe things can be accelerated. And just for reference, the dashed line shows the benchmark for the commercial. Yes, commercial. No, yeah, no, yes. Yes, for commercial OLED, they almost exceed the EQE almost exceed 30%, and the lifetime exceed 100,000 hours. So, well, where are we now with PeLED in 2025? If you look at this table, the best reported EQEs have reached 26% for blue and 31% for green, and over 32% for red and near-infrared. These numbers are already on par with OLEDs in many cases, and that's something we could even imagine a few years ago. But of course, there's still a big gap in the T50 lifetime. Right now, it ranges from hundreds to maybe a few thousands of hours, depending on the device and the conditions. That's still far away from what we need for commercial applications, which is more like tens of thousands of hours or more. And so another thing people always concentrate is a toxicity issue, especially with lead. It's something that the community is working hard to address. So how about the future of PeLED? At the moment, at this stage, nobody knows whether we could really make it in the market. But let's look at curve on the right. According to our previous technologies, I mean any technology, they all progress slowly at the beginning stage, and they boost up quickly at some point. And so now the question is, are we at the tipping point? Are we standing just before a technological explosion? We don't really know, but what we do know is the EQE is already there, and the interest is there, and the progress is fast. So it might be closer than what we think before. So nobody knows exactly when PeLEDs will hit the market, but if it happens, it could happen very fast. So we would like to say, let's get ready. It is time to develop PeLED with a really commercialization-oriented perspective. So for a long time, we have been focusing on technological development because all the perovskite works we are physicist, chemist, or material scientist. So we pay attention to much on the from the material or the physical perspective. But we rarely think about with our technological road can really compete in the market. I mean, from some market perspective, the current business model requires more than just good technical performance. We need to consider three key parties, the coordinators, usually government or policymaker, who care about the legislation and environment and the resource use. And the second party is a seller. That's a company who cares about the cost and profit. And of course, the buyer, the customer who simply wants performance at a reasonable price. Therefore, a successful transition from lab to market should consider three key aspects: environmental, economic, and the social impacts to make these three parties happy altogether. In another word, we need to think about the sustainability. Achieving sustainability requires us to think from a life cycle perspective, from how we make the materials to how we use them and how we dispose or recycle them. Otherwise, we are not really solving a problem. To really understand the sustainability of a technology, we need more holistic tool, and that's where life cycle assessment or LCA comes in. So the motivation of LCA is very simple. It assesses the environmental impact of an object have on the world from cradle to grave. A life cycle of technology includes everything from extracting raw materials, manufacturing the product, transporting, using, and eventually disposing or recycling. The typical four-step process of an LCA: first, we define the goal and scope. What are we assessing and what do we include? Then we collect all the inventory data, like how much energy and materials are used at each step. Next comes the impact assessment, where we translate the data into environmental effects like carbon footprint, toxicity, or resource depletion. And finally, we reach the interpretation, where we try to make sense of it and make some decisions. So LCA doesn't just tell us how green something is, it tells us where and how to improve it. It turns sustainability from a slogan into something we can actually quantify and act. Since LCA was initially invented to assess the energy technology, so some of you guys probably have read it in some perovskite PV papers. So in the PV area, LCA has been used to evaluate like toxicities, environmental impacts, compare different energy technologies, and identify hotspots. It also spoke the eco design and the idea of circular economy, helping researchers and companies think about recycling, reusability, and resource efficiency. For example, one of the work by our group published in Nature earlier this year have a well-used LCA to design the recycling strategy of perovskite solar cells. And more importantly, LCA provides quantitative metrics which are super useful for policymakers and even investors who want to understand whether technology is truly sustainable. So the method is very good to be applied for perovskites, but almost not at all in PeLEDs. And that's exactly why this work, applying LCA to PeLED, is both timely and important, we believe. So now let's start the section of LCA of PELD. Here we show the life cycle of a typical PELD device from manufacturing all the way to the end of life. This is what we mean by from cradle to grave. The goal is to understand how a PELD affects the environment and the society throughout its life. And for this work, we focus on the assembling process, meaning we include how raw materials are used to make the device, but note how those raw materials are produced in the first place. That's our system boundary. And we starting with the raw materials acquisition, like ITO glass substrate, perovskite emission layer, transport layers, electrodes, and encapsulates everything we need in our lab to produce a PLD. And then comes the manufacturing stage, which includes spin coating, annealing, vacuum process, and so forth. And all of which require electricity and may release emission. After that, we consider the distribution, then use like in lighting or displays, and finally the end of life, recycling, landfill, or disposal. So this model allows us to trace emissions and energy use across each step, and more importantly, to ask where can we improve. Now, once we had our life cycle framework in place, the next step was to ask which PELDs should we actually evaluate. So we wanted to make sure the analysis was meaningful. So we didn't just pick a random device. Instead, we follow a few clear selection rules. So first, the device need to have a high QE and high luminance power efficiency. But most of the previously published paper never reported this value for some reason. I have no idea. But so we have to determine that by ourselves, and we select some quite representative technologies. And also, you should have a decent lifetime and representative structure to make sure that our results can be widely used in the future. And lastly, we make sure to cover all the full wavelength range from blue, green, red, white to near-infrared, almost cover all the mainstream applications. So in the end, we selected 18 PELDs for blue, for green, for red, to white, and for near-infrared. And these devices represent the current state of the art, both in terms of efficiency and practicality. So they serve as a really solid base for life cycle analysis. So now that we have the assessing objects, and the next step in LCA is to build the inventory, basically a very detailed list of everything that goes into and comes out of the system. So in our case, we used unified function unit, 2 square centimeter PLD with 50% active area. That means all the inputs and emissions are normalized to this representative device. And this is also a typical size for perovskite solar cell device in the lab. And the inventory also include 2 main types of data: materials and the electricity input, and materials and electricity emissions. The material things include like glass, solvents, precursors, transport materials, and so on. And the electricity is consumed during the fabrication. And here I show 2 actual examples. All the data comes from the lab. The table lists out every step, like how much acetone is used to clean the substrate, how many milligrams of perovskite precursor are needed, and even the spin coating speed and the annealing temperature used during the fabrication. So once we have selected our representative PeLEDs and collect all the inventory data. The next step is to actually calculate the environmental impacts. For this, we use a widely adopted tool called CIMA Pro software together with EcoInvent database. So it's one of the most common LCA software in both academia and industry. And this diagram here shows a basic workflow. On the left, we input our life cycle inventory. That's a detailed in material and energy data we just discussed. Then CIMA Pro connects that to the database, like how much carbon dioxide is typically emitted per kilowatt hour of electricity, or how toxic a certain solvent is. And next, we build a life cycle model to apply an impact assessment method, depending on which types of environmental effects we want to study. Like include, for example, the climate change, ozone depletion, human toxicities, and many others. And finally, we get results that we can interpret and compare across different devices, process, and design choices. Yes. So now we are run the impact assessment. Let's take a look at what the results actually tell us. So this chart shows environmental impact distribution for 4 different types of high-performance green PeLEDs. And as you can see, not all PeLEDs are created equal, but they have the similar efficiency across the 18 middle point environmental impact categories. We identified eight significant impact areas, mostly related to the toxicities and the global warming. For example, we see strong signals in human toxicity potential, both cancer and no cancer, as well as freshwater and the marine ecotoxicity. And yeah. So based on this, we are able to go into the further details. So here we show the 8 most significant environmental impacts across blue, green, red, white, and near-infrared PeLEDs. And we also break down where the impact comes from, including raw materials, device assembly, landfill, and transport. So overall, RGB and white PeLED exhibit comparable impacts because of the identical device structure. The variation in material and electricity consumption for the transport layers or perovskite layer are insufficient to cause the significant difference. And the primary contributors of the impacts are raw material, particularly organic cleaning solvents like acetone or isopropanol. The remaining impacts come from the device assembly, pretty much from the vapor deposition process. Near-infrared LED show very large impact due to the use of gold electrodes. Gold has a very high energy consumption and pollution associated with gold mining. So this slide tells us organic solvents, especially cleaning solvents and gold electrode in near-infrared are the largest cause for the environmental impacts, much more than lead. Toxicity is always the largest controversy or concern for the perovskite devices, but normally it's our concern about lead is just an intuitive conclusion and the lacking of a real data supported. So here we want to evaluate the toxicity of PeLED across the entire life cycle to check the effect of lead. In short, I just skip the process, but in short, we find that the lead-related toxicity only contributes about less than 1% of the total environmental impact in the full life cycle. That's very far lower than what many people might expect. And it's primarily because the perovskite layer is very thin in the PLD device, and the amount of lead we used in perovskite is very minor compared to other layers. So in contrast, some heavy metals like gold or cesium even contribute much more to the toxicity if you use too much. So in summary, yes, lead is toxic, but if we lead is toxic, but we actually in the actual production we didn't use it too much. And if we want to make green PLDs, we need to always consider the entire life cycle chain, and we need to consider the utilization amount. We still simulated the benefits if we treat the lead by lead recycling or waste treatment. And just briefly, if we use some recycling strategy, we can reduce the human no cancer toxicity to a certain extent by almost by a factor of 2 or 5. So that's pretty substantial. Now we have already pinpointed the main environmental hotspots in PLDs. The next step is how we actually fix them. So we identified and simulated 6 to 7 technological mitigation strategies. Like for RGBs, we can see that the reusing cleaning solvents, recycling substrates, and the optimization vapor deposition can each reduce impact. And when you combine all of them, the impact drops by more than 50%. And for near-infrared perovskite LEDs, which we know suffer from high impact due to gold. So the single most effective fix is replacing the gold electrode, which brings down the impact by orders of magnitude. So that's very huge. So in summary, these technical strategies offer a clear and achievable path to greener, industrially scalable PLDs. Considering the priority, replacing gold electrode for near-infrared is the most important. Then it's reusing clean solvents, recycling substrates, waste management, and vapor deposition. In order to evaluate the competitiveness, we compare the environmental friendliness class of PLD to other commercial technologies. So in the lighting market, the current lab scale PLDs already perform better than traditional lighting, like you see, compact fluorescence lamp and gallium nitride LEDs. And if we apply those optimization strategies we just discussed, then the future industrial level PLD become one of the most sustainable options. In the display market, OLED still perform best, and then followed by the future PLDs. They both do much better than the LCDs and the QD LEDs. So to sum up, PLDs are not just efficient and colorful, they are also promising candidates for eco-friendly lighting and displays. Besides eco-friendliness, economic cost is, of course, another critical factor if we ever want to bring PLDs to market. So we estimated the production cost of different PLDs. We can see that for most gold-free PLDs, the total cost range between 70 to 800 to 180 USD per square meter. However, the cost for the gold-based near-infrared device jumps to almost 319 USD per square meter, more than double. The second biggest cost contributors across all PLDs are the whole transport layer and the electron transport layer materials. And then follow up the power consumption, especially in some energy-intensive process like vapor deposition. But the overall summary is still promising. Even at this stage, the cost of PLD is already about half that of OLED, and that gives a PLD a real competitive future in the market. So now we have have already discussed both environmental and economic cost. Let's move to another key parameter, lifetime. The T50 lifetime has already become a very good technical indicator to evaluate the stability. For sure, the longer technical lifetime is always great, but in reality, we can't make the technical lifetime last forever. So we must have another lifetime indicator to tell us how long the lifetime would be sufficient, which means a minimal requirement for the lifetime. The T50 or T90 lifetime means like a limit requirement, the limit, and now we need a minimal requirement. So here we introduce a new parameter called RIMT, or relative impact mitigation time. It essentially evaluates how long a PELD needs to operate in order to offset the environmental impacts of producing it. I have to skip the interpretation of the formula and the calculation details because it's a very long story and we don't have too much time. But you can, if you are interested, you can read our paper for the details. Just in short, so if we want to offset the environmental impacts or toxicities of producing PELD, we would better to guarantee the operation lifetime to exceed 10,000 hours level. And this value can serve as a minimal requirement for our PELD. Here we draw a roadmap toward the sustainable commercialization of PELDs. We break it down into 3 parallel roads: environmental, technical, and economic. Each one start from a lab scale to the market-ready products. On the environmental side, strategies like solvent reuse, gold electrode replacement, and recycling are important. And technically, we aim for longer operation lifetime and higher luminance power efficiency. Economically, cost reduction comes from cheaper charge transport materials and large-scale manufacturing. So here is a key message: achieving sustainability isn't just about make the technical performance better. It's about balancing all three parties. So to make the regulators to see environmental compliance, to make the manufacturers to see the economic feasibility, and to make the customers to see reliable and affordable performance. Based on our previous conclusions, so here I briefly show how these findings guide our future work. So currently we are trying to do some efforts. First, we are working on a new device structure, not only to reduce material cost, but also to enable the large area fabrication beyond the 20 square meter, which is crucial for scaling up. Our target is to keeping the EQE at the same level, but cutting down the cost by maybe 1 order of magnitude, and reducing the environmental impact by 1 to 3 orders of magnitude. So far, I would say that we are still on the way, but step by step towards a sustainable commercialization of the PELD, and we believe it will not be too far away. So let's now summarize everything up with a few take-home messages. So first, our life cycle analysis show that current lab-scale PELDs already demonstrate promising environmental friendliness, even without full-scale industrial optimization. Second, we often think lead is the biggest issue in perovskite, but that's not the case here. And because in practice we use very minor lead in perovskite, and I believe that these results would be very similar in perovskite solar cell cases. And so my opinion is let's be confident to lead-based perovskite technologies. Instead, organic solvents and heavy metals electrodes like gold pose a much greater impact and should be handled with caution. Third, our work identifies several practical strategies to mitigate these impacts: reusing solvents, replacing gold, scaling up fabrication, recycling. By combining these strategies, we can bring PLDs to a level of eco-friendliness comparable to OLEDs, and economically, this the outlook is still positive, and we estimated the fabrication cost of a commercial PLDs to be half of OLEDs, which makes them very attractive for the market, probably. And finally, on the life cycle, on the lifetime side, we recommend targeting over 10,000 hours of operation to compensate for the environmental impacts. So I'd like to acknowledge the people and the organization who made this work possible. And scientifically, this has been a collaborative effort between Linköping University and Shandong University. I'm especially grateful to my supervisor and courses, Feng Olof, Jia Honglin, Jia Shuo Xiaoting. And financially, we were supported by the Swedish Wallenberg Foundation and the USA SVCF Foundation and the Senado. So without their funding, this work would not be possible. And I'm currently based on the Department of Physics, Chemistry, and Biology at Linköping University. And if any part of today's talk sparked your interest, feel free to connect with me. And I'm always happy to discuss and exchange ideas. And also, thank you so much for your invitations from Bowen, Simon, and Vincent. Thank you for organizing such a great series. And thank you for your attention.